Hello, gentle readers. Reading Foundations today, about February 10, 2026. What has been the ongoing in these Reading Foundations essays is connecting and relating the contents of various scientific, mostly works, or if not necessarily so, about the theory of science and the applied, the theory of physics or mathematics and logic, and for the model theory, that being equity interpretable with proof theory, and overall generally sort of the account of the dimensional analysis for physics and these kinds of things. What was left off reading here was Routh's Routh's Advanced Dynamics of a System of Rigid Bodies, or for kinetics and kinematics, sort of as related to the distinction here that's made between kinetics and kinematics, and that it's in most of its occupation is as of in the consideration of the invariants and the ideals, and the practical results, the empirical results. The result is after that for the exchanges of things, and the energy is kind of a pointwise particle, and the entelechy of things, the connectedness, the continuity of the things. And then overall, then the invariant is usually intended to reflect that invariant is the same thing as there existing a symmetry, is the same thing as there existing a conservation law. That the continuity laws are a bit broader and intend to subsume, to include what's the usual notion of conservation law as making all matters of balance in the invariant theory of invariants. That the idea then of the continuity law including that, and yet being broader, is to take into account that the considerations of the open and closed in the physical systems, that formally and nominally it's an open system, the physics. And so it's only in particular the contrived instances, the classical, the closed itself. And so some of the accounts of about the implicit parametrizations of things, or parameterizations, if I'll distinguish metrization and meterization. For parametrization and parameterization, this was discussed here some time ago, has that the implicitly infinitely many quantifiers in front of any a term are also related to things like the infinitely many higher orders of acceleration, and otherwise just kind of the more thorough account than is usually given, or maybe even can be given in the classical accounts. And then that almost always reflects back on the classical exposition of the superclassical, or Zeno's arguments, the archer, the Achilles and the tortoise, the stadium runners, and these kinds of things, about why then beyond just the very basic notion of induction applied and counter-induction for co-induction, either way to confound itself, to contradict itself, then there's the account of deduction that makes for then it must be truly a complete sort of infinitary analysis and infinitary reasoning to make it simple and clear that it can be reasoned, these truths about the objects of continuity and motion. So then here for that there's quite a more extended treatise in the moment in motion, of course, about that, trying to figure out what would be the most relevant sorts of terms about the centrality and primariness of otherwise what's the observables and the measurables, makes for an idea of how to arrive at what's furthermore the unlinear. So the linear is just generally reflected as what preserves the usual notions of the shortest distances, straight line, and right angles, and with regards to the quadratic and the triangle inequality, or Cauchy-Schwarz inequality, as it's called. This establishing what makes for a system of inequalities, making for a means just like delta epsilonix does to establish via induction that something would go to zero. That these establish that something is no different, as for the limit of these things. The quadratic in the areal terms, about the areas of things vis-a-vis the lengths of things. So this sort of account, while not saying much, as well is about then some examples that I thought would be kind of relevant to talk about. This one's about the lever, the simplest machine, and its usual accoutrement of the ideas of a fulcrum and a lever and the application of force is to either side, and then according to the moment arm, then the how one would say the mechanical advantage so afforded is by machine. That machine's description basically describes what is the advantage that such a device as a pulley or a ramp, the inclined plane, the screw or the lever, otherwise the simple machines provide. And then as for the complex machines, how and why those begin to differ from the simple enough setups that where force is always basically opposite, and how that's applied then to the angles, the usual notion of the vectors as the sum of vectors in the directions given according to coordinate setting, and then about how and why then for something like the lever, for an account of something like Hooke's barbells, they're called, or Hooke's dumbbells, weights. Usually the idea of is with a bar and then on either side of it a weight, and usually symmetrically an equal weight, as used by weightlifters to test their strength in exercise. So Hooke's law is as after about springs and pendulums, and then Hooke's barbells is in the idea of in the study of gases or ions, but mostly about the particles, how to consider them when they're no longer merely point-like, as massy bodies, that they're no longer spherical. And so then the idea is this, like, well, instead of looking at the contents as like a point particle, it's like, well, then abstractly it's going to have a response when each of these collide that is not as of the perfectly inelastic collision of bowling balls with no imparted spin at all of the same size, and basically also all at the same rate. Then the idea of how that is unlinear is that there's eventually involved a model of how it starts spinning and is always spinning vis-a-vis the most contrived sort of idea that its circular motion is zero. And so these are the kinds of mental models for the models of the things, the descriptions, why then the Hooke's barbells or dumbbells is the idea of then treating things like that, and whether or not that's just applied to mediums like the diatomic models of gases, like hydrogen is not just the free atoms themselves, but always is diatomic, and oxygen is always diatomic, and these kinds of things. Gets into reasons and for the comprehension of why then those are relevant for the statistical mechanics and statistical ensemble of trying to then add up what these expected motions would be when it's formally, again, unlinear. And that's not very tractable. How to make that at first sensible, and then to get into how that's fungible and then tractable. Sensibility, fungibility, and tractability about the tendencies and propensities of the attenuation and dissipation and the oscillation and restitution. So for matters of motion and rest and motion and the moments of these things, why it is so, and these kinds of things. So I just thought to mention that as an example again of the idea of any consideration of the point particles with regards to the kinetics and kinematics as arbitrarily not perfectly inelastic collisions, and yet as well as never ever actually interacting as by the surfaces of spheres, but always as by kind of the rough application, or Maxwell's hammers is what I came up with, as if each particular item was covered with miniature hammers, like for the centripetal and centrifugal. That's the idea of the centripetal, is like kicking around a potter's wheel or something like that. That these are just sort of some ideas floating around as to why those are relevant to a description then of otherwise point particles, since eventually that just kind of runs out, and with regards to the notions of motion, like Brownian motion or random motion, and the including then furthermore the adiabatic and non-adiabatic, and ideas from fluid and compressible flow, whether it can be modeled as anything that crosses an area as long as the sum is equal to a constant for a constant rate of current. That the eddies, whorls, ripples, and vortices come and go all the time, and they're constantly auto-annihilating, the usual idea being, in their creation and destruction, while at the same time it works out the same classical invariant on average in the mean in these kinds of things. So that's it, just to be said that for models of current and flow, and flow and flux, where flux is given the usual idea of flowing the other way, even if it's superconductive and of zero mass or infinitesimal. Why those things are part of the balance and the exchange of the creation and destruction, otherwise conservation, of current and these kinds of things. So flux then also is related as to usual accounts of in an area when something goes from spherical to flat, like the solder's flux and so that the name still applies. And then for the Gaussian influx, that's another usual idea of current, because it's for potential, and it's also again another idea where it's like, yeah, that's kind of funny that, or rather, it's striking that the flow and the flux maintain this sort of contradistinction, and as to why then it's given a fixed place in the definitions of the description, since such a sort of a theory as would claim to model something, meaning to embody it structurally, has constancy and consistency, completeness, and then concreteness in this sort of way. So flux is then, after the idea of this Maxwell's hammers or Maxwell's levers, after Maxwell's demons, an arbitrary gate between an area of higher or lower entropy, and then in the random motion just kind of opening and closing with regards to whether it could affect a temperature differential. That being one notion of entropy. The other being that things like the Peltier junction, any kind of junction in effect, implements one of these. And then that Maxwell's levers and Maxwell's hammers are for Mach or for Hooke or these kinds of ideas, is that then those get placed in terms of where those are intended to describe the activities of the particle model, which is in effect the statistical ensemble. And for thermodynamics, it is the theory of physics, with regards to where kinetics are considered kind of first, instead of the electricity is considered kind of first. And as described here, that can be broken down further, and then they either is kind of effectively whatever's in effect as the mass term, and that the usual mass term is mass vis-a-vis charge, and then with regards to the nuclear and these sorts of ideas, the tetrad of quantities. That then, getting along with these books, then the kinetics and kinematics are have that the kinematics is a richer account, and so momentum isn't conserved anymore. it's still conserved only in the classical infinitesimal pointwise, pairwise, ideal particles, and that, but it's also ideal, and it's more practical, empirical. That it's never really the case. And so then trying to figure out a general sort of case where what's so is like so, the unlinear is then to equip models of material objects as connected by rigid rods and always as having a moment arm themselves. So particles as dimensionless or particles as dimensioned. And then about the pan-dimensional and polydimensional and matters of continuum analysis and continuum mechanics, that these are some of the concepts in play here, because the standard account is just absent them, and it's thus incomplete. And then furthermore, particularly and especially because the empirical doesn't really bear out, lacking these sorts of accounts. So that's can make for a greater account of these sorts of ideas, and when and where and why, like in Hooke's law, for example, or some of the ideas of the quasi-invariants that are empirical and in effect, or anything to do with junctions, for example, or entropy vis-a-vis organization, its usual term, has that these are all in effect and observable, measurable, and of course the other notions relevant to after reproducibility, observability, and measurability, the science for the data. Let's see what's in the box then. Let's see. Decisions with multiple objectives, preferences, and value trade-offs by Keeney and Raiffa, Keeney, and Raiffa, Raiffa. So decisions with multiple objectives, preferences, and value trade-offs. So kind of like talking about Maxwell's theory and the Maxwell's demon about entropy and kinetics and thermal second law and these kinds of things. Then is, for example, the differences between when it's just a box where it equilibrates pressure, or when the equilibration of pressure also changes the a balloon, say, or a volume of area according to an ideal law of pressure in the compressible, and that these are the kinds of things. So this decisions with multiple objectives also speaks to things like when the objective is gain, say, and then there are multiple ways to gain. For example, one of them not being losing. And so that it can be abstractly said that in a game, there's always two ways to look at that, winning and not losing. And also, similarly, it's possible to take for statistics the very idea of probability itself and estimation, the probability and the uncertainty, or chance and uncertainty. And so that makes for it then. For example, as was being read from the last episode about Hookean independence or Mach infinity. I was reading that for M infinity. It usually isn't counted. That's a signal for Earth, the letter. But Mach infinity, the Mach numbers, and how those are effective and practical vis-a-vis when they're just the floors of things or the ceilings of things, is kind of like the extent of the compressible and incompressible. When, for example, it's given for Newton's approximation of air resistance, that it's after Hooke's law, an account of the approximation. That then having for chance and uncertainty, and the idea that the reflection of those things has that one of them would be they're between 0 and 1, both of them, and so one of them at a particular stable equilibrium is 1 minus the other one. So for A and B, that A plus B equals 1 and 1 minus A equals B, and so and that A and B are greater than 0, say. So with that kind of thing, then the idea is that as one runs out, then it might have a spike, whereas the other one would make a well, or these kinds of ideas. And then that as those tend to converge and diverge to arrive at each other, and then with the hysteresis and the ringing, for example, as can be built from an account of Fourier style analysis, how they would grow according to something like the central limit theorem, and thusly kind of grow towards the mean, the bell curve, the bell shape, and the maximum of the mean, usually over time. Then in other sorts of accounts, for example, with multiple objectives, or as the ideas of this book from Wiley Series in Probability and Mathematical Statistics might intend to describe, has that then that gets into when they're 0 and 1 are the modes, and so the mean being 1/2 would be hidden the fact that it's really a bimodal account of A or B, or 0 or 1 here in this case, about these multiple objectives. And then when thus looking to find whether objectives are satisfied, that it kind of is necessary to run both accounts to see whether the estimates would so hold that both winning and not losing would hold. And so that's just not the usual count. Sometimes there's not enough data, one might imagine. But at the same time, it's formally, nominally, always part of the model. So that's just an example of one of these things that gets into having that as already given is like, look both ways before crossing the street, and these kinds of things, has that these are then what I'd intend to kind of read after the usual development of something like this, up into then why there's more to it. So copyright 1976. The preface begins to read, if we wanted the title of this book merely to convey the subject matter, it would be some horrendously complicated concoction such as on cardinal utility analysis with multiple conflicting objectives, the case of individual decision-making under uncertainty from the prescriptive point of view, a special emphasis on applications with a little theory thrown in for spice. Our actual title, Decisions with Multiple Objectives, Preferences, and Value Tradeoffs, is longer than we think a title should ideally be, but unfortunately is too short to prevent unjustified sales. Even in such a simple case, it's not so easy to balance among the conflicting objectives, convey the subject matter, minimize the length, and promote justified sales, but prevent unjustified ones. To an ever-growing niche or circle of people, decision analysis has carved out for itself a niche in the literature of operations research, systems analysis, management sciences, decision and control, and cybernetics. Decision analysis looks at the paradigm in which an individual decision maker or decision unit contemplates a choice of action in an uncertain environment. The approach employs systematic analysis with some number pushing, which helps the decision maker clarify in his own mind which course of action he should choose. In this sense, the approach is not descriptive because most people do not attempt to think systematically about hard choices under uncertainty. It is also not normative, since it is not an idealized theory designed for the super-rational being with an all-powering intellect. It is instead a prescriptive approach designed for normally intelligent people who want to think hard and systematically about some important real problems. So here the notion of like the decision analysis and the decision maker is a little bit different than the usual account in the theory of the logical and the truth of the truth maker. The truth maker is then that which is essentially, so according to the logic, it makes things so. And then from a teleological account, that exists. This is our Comenius language that has all these truisms in it. Then the idea of the decision maker is it kind of is where we hope to make decisions, not compromises, although it's oftentimes enough the same thing about winning and not losing, compromise vis-a-vis decision. But they do have a distinction in their terms, just like chance and uncertainty, decision and compromise. So about then the decision maker and vis-a-vis the truth maker is the idea that our practical theories are always making decisions all the time, even if subliminally or unconsciously or automatically. So then the idea of the systematic sort of count for decision making is usually after estimators, where one can gain some confidence that given prior data, the usual idea being, then that attaching that to other theories and relating those to terms descriptively, the description for the representations and the descriptions, then has for the account of probability theory and statistics to make estimators and then relate that to predictions. Has that the usual account is pure probability and statistics. It doesn't have that as a thing, but relating that in terms of prediction theory, that's its own thing because it gets related to otherwise inductively the course of events, which our theory attempts to resolve or help eliminate by making it so that then the theory has already made it so that the events aren't merely inductive and empirical themselves, but after a theoretical account, and that they're seen to agree. And so, that said, then getting into any kind of the usual decision making about empirical accounts is like when a pot handle on the stove is too hot to touch, or is immediately to be put down, those being kind of opposites, but either one being a decision that results in the same sort of outcome. And vis-a-vis the theory of how much heat it should have made, vis-a-vis the possibility, for example, that the adiabatic and non-adiabatic of the range element is not an ideal device, and so that according to a perfect stopwatch, otherwise, and a perfect measurement of the range element, that and an estimate or a monitoring of the current that goes through it, the usual account of range element of various technologies, then that makes for the difference between that and just the decision making, which can be immediate. And so then the idea of these systematic accounts gets into more about the ideas of like, well, these are the numbers that we can use to crunch to make rational decisions according to these numbers, and in a fungible means and then a tractable means, then to put that up, for example, to computers to apply this sort of information advantage vis-a-vis what makes a computational advantage, those being machines then again of sort. Decision making. The theory of decision analysis is designed to help the individual make a choice among a set of pre-specified alternatives. So that basically reflects on the statistical hypothesis and the statistical validity according to the null hypothesis and rejecting the null hypothesis. So that's the alternatives and those recursively. Of course, decision analysis analysts do admit that an insightful generation of alternatives is of paramount importance. So this is a notion of intuition and kind of knowing the problem space. They also take note of the often overlooked fact that good analysis of a set of existing alternatives may be suggestive of ways to augment the set of alternatives. For example, the correlations. But this is a side point that is not suitable for development in a preface. What is important here is that the usual analysis, after suitable modeling has been done, involves two distinctive features: an uncertainty analysis and a preference or value or utility analysis. So that speaks then to preferences and value trade-offs about winning and not losing, and for example, like how hard or how soft and these kinds of things. The present book helps improve the balance. In comparison with this voluminous literature on the uncertainty side, little has been written about the value of or preference side of the picture. At present, this gross imbalance between the value and preference side and the uncertainty side is also unfortunately very much in evidence and applications. Several person-years of effort will be utilized developing, modifying, and verifying an elaborate simulation model that outputs the possible levels of several indicators of interest resulting from any particular policy. Perhaps the output is synthesized in terms of a few graphs or tables, and a summary report is written for the decision maker. This decision maker then struggles for perhaps a week with the implications of the alternatives and then chooses an alternative. The score: person-years on the uncertainty side of the problem, a week on the preference side. We feel that the shifting of little effort, perhaps only a few person months, to the preference aspects could lead to significantly improved decision-making in many situations. In this book, we suggest how you might constructively use more of the effort on the preference aspects of analysis. So here that might be related to preference aspects of pleasure and pain and hope and fear, those being usually what could be possibly used to gauge yes or no whether something is to be so, with the usual idea of seeking one and avoiding the other, or not avoiding one and not seeking the other. Again, making for a balance of the terms and always a reflective sort of inversion of the terms vis-a-vis the sort of one-way street of the principle of non-contradiction, aka the principle of explosion, and ex falso quadlibe, instead this greater, less quasi-modal ex falso nihilum. So then looking at this, then we'll get into that. The idea is that there's summary. So after statistics is summary. And any sort of statistic is both a statistic and a summary statistic. And then any kind of collection them together by any kind of means that can take a sum or form a mathematical structure of them is, again, a statistic and a summary. So summary statistics are a great sort of count. For example, the average, the expected value is even a sort of those among all possible distributions of a distribution of distributions for probability theory, or as from a distribution of the shape or scale parameters, or these sorts of things among probability distributions, for examples. The summary is a great sort of thing. And then that also speaks to the great implicit statistic, always so, the time series or ordering statistics. That being also as well, always so, then time series and ordering for the samples, also as statistics, and then as of the, how one might say, of the values. Again, is that's kind of on the right hand side of this of the margins of this balance book between all the data and yes or no. So these are the kinds of things. Office to naval research. So operations research type of stuff. Contents: 1, the problem. 2, the structuring of objectives. 3, trade-offs under uncertainty. Curves, ordering, margins, cases, rates, conditions. 4, unidimensional utility theory. So that would remind me of Samuelson and Samuelson's utility function, these kinds of things. An economist who basically says it's kind of like adding things for you. It's like, well, what is the cost to get something in here? Well, what's the cost to take the old one out? You know, adding everything's got to be included in these kinds of things. 5, multi-attribute preferences under uncertainty, the 2-attribute case. 6, multi-attribute preferences under uncertainty, more than 2 attributes. So here I'd relate that to Ramsey numbers and the difference between 2 and 3. So you might say, well, obviously 2 and 3 are different because 2 and 3 are not the same number. Yet under asymptotics, one also might have heard is like, well, obviously 2 to the x is no different than 3 to x. It's infinity. So it doesn't matter, but it's always greater than, say, x squared and x cubed. The difference between the powers are quadratic and the exponential. Yet at the same time, between 2 and 3, a lot of things change between the combinatorics of the pairwise and the combinatorics of the triple. And so, and then that grows and broadens, but there's a qualitative as well a quantitative difference between 2 and 3 in the sense of combinatorics. So for Ramsey numbers, that gets into differences and considerations why that is so. And similarly in terms of the considerations, the pointwise and the pointwise, the pairwise, and then in getting in terms of like the 3-body problems, or as I led to study a little while the other day, Lagrange's 3-particle principles, helping explain that it automatically kind of steps toward the illative or Martin's axiom or univalency, infinite union after pairwise union. That's just a point. Then when the authors of this book are getting from like, well, there's one preference to, well, there's two attributes, and now there's three. That's why these chapters eventually have to. That's the things you might start seeing breaking down and out of these of the combinatorial explosion. 7, illustrative applications. 8, airport development for Mexico City, a case study. I flew into Mexico City one time. 9, preferences over time. 10, aggregation of individual preferences. Bibliography and index. Investments independent of asset position. Proportional risk aversion. So this is the winning, and I was like, well, since we're not starting at 0, how about not losing? These kinds of things. Again, it's very simple to convince things that are good by just saying, here's the latest number, it's good. Unless they have a memory, or they anticipate further distinctions from that being so, or the anxiety and the fear of it. Chapter 6, multi-attribute preferences under uncertainty, more than 2 attributes. The chapter parallels that of Chapter 5 with the distinction that here we are concerned with multi-attribute utility functions with more than 2 arguments. Also in this section, we discussed procedures for assessing a multi-attribute utility function without first specifying the functional form. See, when you only have 2 attributes, kind of like when we were talking about the A and B before, it's always so that you can compute B that it's 1 minus A. But now when you have 3 attributes, it's different. So, and that's just another example of how these things make it so that, well, what was like, it's kind of like when you start with having elements and attributes in a schema of a data type or something like that, or a user-defined data, or abstract data type. It's like when the attribute goes from being just a relation, just an attribute, to being a vector, it's like one or more. Or according to the cardinality of the attribute, how many it has, it entirely changes the access-patternry. So then to make it so, it's like I'm always going to just treat every attribute as multi-valued, and particularly including the case for when it's always exactly 1 or 0. That's enough general purpose then that it can treat everything that same way, vis-a-vis just being able to ingest a block at a constant rate. It still becomes a constant rate, a slower constant rate, over the linear to kind of keep that stuff together, but it just helps make another account of why there's a difference cardinally between 2 and 3, including in the asymptotics, and as about what's termed Ramsey theory, rather loosely. But that's where it lives, kind of, because that otherwise there's aspects of fields of mathematics like asymptotics who says that's exactly what we say erases the difference is in the limit. They're one or the other comparing an exponential to a quadratic or a polynomial function is having an inequality there, and then all such manners of systems of inequalities, which affect to relate that the equality relations of one under the other do hold. Again, just another example of reflection and inversion and these kinds of things. The chapter immediately begins to speak to why these things vary. As indicated here, these procedures are valid for 2 and more than 2 attribute problems. Therefore, these new procedures. Overview of the chapter. Applications, attributes, sets of attributes, complementary sets, preferential independence, and utility independence. And that gets into correlation and anti-correlation, and then also is non-correlation. Consequences, utility. Another example that the non is not necessarily the anti. Independence concepts. And then getting into more definitions of sets, and then product terms, and the combinatorics and counting arguments and these kinds of things. Relating that to geometry and area and volume, combinatorics, recursion, counting arguments, sums and products. and the like. If, in addition to the requisite assumptions of Theorem 6.1, the decision maker is indifferent between a lottery yielding either this tuple or the other tuple with equal probability, or a lottery yielding either this other tuple or this other tuple with equal probabilities, the utility function must be additive. If he is not indifferent between these two lotteries, then the utility function must be multiplicative. So here they've built it out that they have a difference between the additive and the multiplicative, and what that means for the arithmetic is something that speaks to then in Theorem 6.1 it would be relevant. Not necessarily having that right in front of us, then trying to figure that out is like, well, otherwise the additive and multiplicative would not necessarily be so different, because we'd figure them that they would compose the same way, whether it's like a sum or product, and then is whether it's just like 1 minus b or whether it's 1 over b, and whether then that goes to 0 or goes to 0. Figuring that if they're otherwise the same, then they kind of have to end up having the same kind of result underneath the applications of the arithmetic generally. And then the idea of saying, well, our arithmetization is going to do this in numbers, so it's using the additive or it's using the multiplicative. It's a very strong way to do things, because as much as you can make an arithmetization of things, you can just use machine numbers and machine arithmetic. And similarly for an algebraization, you can make an arithmetization of things and use machine number and machine arithmetic. And especially when you have a difference between the additive and the multiplicative, you can start taking, when it's possible, the differences between the laws of, for example, 0 is the additive identity and the multiplicative annihilator, those being opposites and quite unrelated, otherwise basing on the left or right hand side, and when the ordering becomes significant in the application of these terms. So this makes me happy that this treatment from the late 60s and early 70s has already got it down to basically numbers and an adding machine. And furthermore, it's a little bit also about counting arguments just to tally these up. And it'd be a different sort of account than the usual accounts given to, say, inductive accounts of predicate reasoning on algebra, because it's arithmetic from the get-go. And so that's also a good thing to put in play. It could be very well used in the learning algorithms, say. So now I've noticed that it kind of has a basic approach to an arithmetization after the description, and then the arithmetization of the terms. So then they can be treated according to arithmetic and having number values, numerical values, and as of the arithmetics and algebras and these and like, what the limitations of those would be. For example, is like, oh, well, they're always between 0 and 1, or they're always non-negative, or they're always between -10 and 10, or these kinds of notions of the conditions where the constraints hold. Then that's getting into some of the ideas. For example, 9.4 says relaxing the independence assumptions. It's like, otherwise they can't be relaxed. It is strict, not lax, to have these otherwise throughout without loss of their generality. But then getting here is like, well, without loss of generality of some of the other kind of ideas, then these conditions can be let out. These independence assumptions, assuming any correlation in that at all. When one could argue is like, well, either if something is actually correlated, then they're only one event, and then when they're not, then however much as that they're two events, then they're independent. That is arbitrarily so. The decision maker as synthesizer or amalgamator, and so that kind of gets into two ways to look at those two things invariously. Because whether it's making something out of nothing, or whether it's only bringing together those things that already exist, and whether that includes internal or external things, has that these two words otherwise have a pretty common meaning together and a shared meaning, and then how they're to be distinguished is how they're being brought together, or what they serve as the summary. Summarizer as synthesizer or amalgamator. Pure cases, uncertainty model. complications, participatory group, related work, game theory. So they mention of closer concern problem posed in chapters the work of Arrow, 1951 and 1963, on social choice and individual values. In Arrow's seminal work, however, he considers only a finite number of alternatives, and each affected individual simply rank orders the outcomes according to his preferences. The problem is formulated by Arrow, but does not bring in the individual's strengths of preferences. It's captured by a full utility function. And according to what their utility function may or may not be as of a continuous range of values, vis-a-vis just an arithmetic expressions, is also that would also be a bit wider than this too. The problem is formulated, does not bring strengths of preferences. Routh and Raiffa review Arrow's work, and in section 14.6 of the book they discuss some attempts, mostly that of Hildreth, 1953, and so on. Then here into the bibliography, there's about utility, measuring utility, evaluating time streams of income are D.E. Bell in 1974, and D.E. Bell again, a utility function for time streams having interperiod dependencies. D.E. Bell, A. Blomstein, the landing capacity of a runway. G. Carter and E.L. Ignal, 1970, a simulation model of fire department operations. J.P. Collins, 1974, the development of a solid waste environmental evaluation procedure. N.C. Dalkey, 1972, Studies in the Quality of Life, Delphi and Decision Making. Interactive Goal Programming. J.S. Dyer, Management Science, 1972. So, for expert systems and then decision support and the decision making, this is an example of decisions with multiple objectives and hierarchical preferences, and as well preferences that are their own model of acceptance criteria. Formal methods, usual idea of formal automata is an acceptor or a rejector. And then the idea kind of a usual kind of like, well, sure, meaning yes, and then no, meaning a rejection. And then maybe, I mean, if there's not otherwise a reason why not, you know. Then making for that's the usual way then to add predicates to the filter objects and attributes of those. For example, when building one for a data table on a web page, or as a short format to pass back to a query on the server side to filter that out as well. Yes, no, maybe as about acceptors and rejectors is its own little machine, and it's its own little how one might say kind of vector valued approach vis-a-vis Duro 1. A little bit more of the statistics today. Probability and statistical inference. Oh, so this is Hogg and Tanis, H-O-G-G-N-T-A-N-A-S. So from what I understand from Prentice Hall here, this is a textbook, and it's well regarded. Oh, it starts with a bunch of the distributions, discrete distributions, continuous distributions. So the one I had in school is like 2004 or something like that. This is from about 1993, but it's good to see that they already had kind of like the distributions laid out. Because earlier works, oftentimes the distributions themselves were really kind of closely held. And so to find a book that's just like all the probability distributions is fantastic. Because then it gets into like, well, these are known to exist, and somebody's already related them to all these descriptive accounts and run the analyses off them. Then the usual idea is like when trying to do statistical inference, you have a computer and you just run all the distributions against and make all the experiments, and then start seeing which one of those light up, for example, or farming the data out to gather summary as over this distribution of distributions, say. So the distribution tables, or at least when I first found that in a probability textbook, I thought that was one of the greatest things, because before it's like, well, yeah, here's the binomial distribution, or here's like Poisson I got to learn, or here's like the bell curve, or the normal or Gaussian distribution. These are great. Bernoulli, flipping coins. Binomial, like kind of the choice function, sampling with replacement, sampling without replacement. Geometric, it drops off, kind of a thing. Hypergeometric is involved with here that the regular singular points of the hypergeometric function are 0, 1, and infinity. It's defined as f of x equals n1 choose x, that quantity, times n2 choose r minus x, that quantity, over the quantity n choose r. So n choose r at Pascal, I think. How many ways the counting arguments, is it possible to have it so that there are this many samples, events chosen out of the population of size so and so. So n choose r is population choose count, or population choose samples, or something like that. Negative binomial, Poisson, the uniform, of course, it's random. The usual idea of random is it's equal, it's random, it's uniform. Continuous distributions, beta, chi-squared. Chi-squared is after the bell curve because it's also its own thing, but it happens after the central limit theorem. One of the key things is getting up this and you made a chi-squared out of that for analysis of variance and these kinds of things. Exponential, gamma, normal, and the uniform again. So the discrete distributions and the continuous distributions. The discrete distributions where Bayes holds up so well and so great, and then the and conditional probabilities, and so the rule of conditional and joint probabilities, classical, and then the continuous distributions where it still kinds of holds, but just like when talking about a plus b equals 1 and these kinds of things about when they do let out on the kind of the corners, the edges of the box, vis-a-vis that in the middle it's just like if you add them together it's and it's additive, then they have a mean. But for example, when you look at them under a multiplicative rule on the other side, then it could be 0. These kinds of things help express reflect why chance and uncertainty kind of naturally relate to the discrete and the continuous, in a way, and that being loosely, but also as a matter of factly that there are some cases where it's possible to divide them, and when models are one and models the other would make for estimates and invalidations of the hypothesis and not either way. So that's just safe statistics, say, which aren't always very useful, but at least they're not wrong. So yeah, Hookean Tanis have I believe it's a textbook here. Let's see. A junior, senior level course, mathematics, probability, and statistics. It's called probability and statistical inference. So statistical inference is working up the tests and then getting for things like generalized linear models and principal component analysis and gradient descent and some of the other fantastic tools of analysis to find minima and maxima and these sorts of things. Then for the tests like Fisher students T and these other kinds of tests, and also just happenstance, opportunistic, looking through all the things, and then figuring out what samples to farm to gather their summary statistics, including enough memory of how to combine those summary statistics with other ones when maintaining median and mode after count, those being the usual sorts of statistics and of an analytic sort, for example, over an otherwise unbounded input data set, mean, median, and mode, and average, and then what it means to be able to then add those together later. For example, say it's like, all right, well, I've computed an average, 6.5. Computed another average, it's 3.5. Together, both those being 1.5 different than 5, maybe you'd wonder, it's like, well, is their average 5? It's like, well, yeah, but the 3.5 was for 10,000 samples, and the 6.5 was for 2 samples. So obviously those can't be just added together and taken, that the average is an average of an average is an average. But if you keep in the summary, it's like this is 6.5 for 2 samples, and this is 3.5 for 10,000 samples. Then you can use you can recompute the average, that way, because you can take the average and then what would have been the sum. And so for the sum and the count and the product, I guess, would be another usual statistic that it's often just kind of ignored. After the count and the sum and these kinds of things for things like dollar amounts or counts. And then for mean, median, and mode, after the average, it's also similar how those sorts of summary statistics, broadly enough, that summary statistics and summary, and then the ability to make it sensible that they're still fungible and tractable, how those can be composed and recomposed, their composability of the statistics is about farming the data and setting up a pretty generic setup for any kind of data to get all kinds of inference rules out of it. Give some example. Oh, histograms are one of the greatest things. It's like show for each item in the population how many there was, the histogram, and then how to order that, how to bucket and group that. Should it be as uniform as possible? Should the line through it be as flat as possible, or the linear regression? Should it have like a quadratic or parabolic regression? How about should it look like the bell curve, which is the usual kind of idea and account of all sorts of ideas? Should it look like a power law? There are lots of different ways to do that, most of which just kind of take right off in doing exactly and only their own thing, and then are completely happy because of the power of statistical inference. And it's close enough for those purposes. Other accounts it would say that eventually is like it's possible, or at least it's possible, simply to contrive examples where those would find the wrong value or make the wrong decision or not provide the correct decision support, or is otherwise having the failure modes. So these are the kinds of things. Bayes' theorem, given page 2 and 10, probability, discrete distributions, continuous distributions, sampling distribution theory, so multivariate distributions, approximations for discrete distributions, getting into limit theorems. The moment generating functions is something to learn more about. These would be probability density functions and cumulative distribution functions and moment generating functions. Estimation estimators, tests of statistical hypotheses. So like what to test and then how to test. Linear models, so general linear models and linear models, and then that's from analysis in mathematics. But then also it's applied directly into these kinds of things. Multivariate distributions, non-parametric methods, review of selected mathematical techniques. So calculus usually. Random numbers on the interval 0, 1. See here the natural unit equivalency function is it is a CDF and a PDF of the integers at uniform random, and that's kind of fun. It's non-standard in a sense because it's not a real function. It has real analytical character, but for probability theory, it's like not only is it a PDF of the integers at uniform random, kind of as if it's more likely to get a higher number, yet it's uniform random. It still has the properties of being as a uniform random. That another one is like it's more probable to get a lower number, but it's still uniform random. It's still the same distribution or distribution of integers uniform random. Another one is they're all exactly equal and identical. And so one might say is like, well, that's entirely antithetical to say that two of these supposed distribution functions exist because there's only supposed to be one according to probability theory. That's supposed to be unique. So it's a distinctness result first, which is like that's non-standard probability now that you already made it non-standard arithmetic. It's like it's infinitary, it's continuous, it's got a reasoning for it. And then similarly with this one, it's like well then how can it be uniform? It's like well because it's a CDF of that as well. So it's cumulative, and that's monotone. And then and the differences are infinitesimal, but just happen to grow, you know. But it does give at least one example of the very qualitative difference between constant monotone and then monotone increasing and monotone decreasing. And then when I say constant monotone strictly increasing, is to kind of leverage those out to be like the way that the uniform natural integers kind of when compressed also make for about the distribution of the unit distribution on the unit interval, because when that is projected through the range of this function, that's also about the uniform distribution of the continuous distribution of a bounded interval, or B minus A. So, foundations of probability theory. Well, all right, then that's about an hour or so. Did a bit of probability theory, probability and decisions. Good day.